welcome to, hello and welcome to the exam 2 review session. What did we cover since the last exam? That part of the equation sheet. Always mean to bring the equation sheet. You should be using the equation sheet, if you're in my class, that is. Or if Dr. Orlip, I think Dr. Orlip uses the equation sheet. I have no idea what Dr. Sahai is doing. Be a good idea. If you need the equation sheet, I could get you a copy of the equation sheet. So you ask yourself, self, see that was funny to me at some other point, and it still remains funny. When you say, ask yourself, and then you go, self, funny, hilarious. What kinds of problems have we covered since exam 1? You should be asking yourself that. Particle, Newton's second law. We did class 6, we did rectangular coordinates, and that was homework 16. Class 7, we had path and polar coordinates, and then we moved on to particle work and energy. So for class 8, we basically did the potential energy, most everything. In class 9, we added conservation of energy, but it's not really adding anything. We did talk about power and efficiency. And then we moved on to particle impulse and momentum. Class 10 should have been just your regular old impulse momentum problems. Class 11 are collisions and the coefficient of restitution. And the debacle, which became homework 11 problem 3 in my class. But let's pretend like that never happened. Okay, so this is what we've covered so far. This is what we covered. That's what this is that homework that 2 should be covering. And I think, by the way, doing this on your own, I did it for you, so you didn't have to do it. But if you were in a class and you were trying to like, what should I study to procrastinate actually doing the problems, this is a good way to get the thing out of there, just to organize your thoughts. And you could even make little subcategories of things and keep track and like leave enough room on your page and take little after you work through some problems and go, there's something I had a hard time with. Here's something over here. I made this mistake and I recognize that. That kind of thing right there. Tell you what, just writing stuff down helps you remember. Helps you organize your thoughts, helps you go through things. Also gives you some priorities like, I'm weak right here. I'm weak right here. I need to get some more problems. And that's studying. I don't like the word studying. It makes you think that you're just reading stuff or watching videos. That's okay as long as you're doing problems and then reading the thing afterwards to try to reconcile what went wrong with the problem, assuming something went wrong with the problem. Because if something didn't go wrong with any of the problems, so you're able to do all of them, go to bed, get some sleep. That too is very important. So here are some problems that I put. Let's describe them as we go through here. I kind of want to do other problems besides these. I want to leave them to you, right? Some aspects that depending on your professor, some professors will just give you a problem, and then you choose what kind of solution strategy you should use. I generally will tell students I would like you to use this because that's what I want to measure on that problem. But just recognize that there is a skill set that would be measured quite often of problem recognition of what kind of solution strategy you should use. I'd like to be able to test that, but my higher priority is can you do So if there, maybe I'd ask 4 problems, maybe, but most of the time there's 3 things. Probably. Although this is a little weird right here. So often it's an important one. And you think about dynamics, right? Because that's kind of an important kind of topic, things bouncing off of each other. I actually tell you, there's nothing more important than the free body diagram. That's like the quintessential engineering tool. So I could ask 2 problems that involve free body. Just because I want to, can you do it? It's also, to some extent, like if you got one problem, I might make some aspect of it a little bit more challenging because I want to see if you could do that. But I'll make the free body diagram fairly easy. And then another problem, I might focus on that free body diagram because I'm trying to measure your mastery of the material, not trying to trip you up. All right, so here's a basic problem. Probably did it in the as an example. I think I did it as an example in class. This looks a lot like a work energy problem. It definitely has it's a pulley problem, so those things are all involved right there. This looks like right away, well, it says at the top there's path coordinates, so there you go. But you see something's rotating in a circle. A lot of times that's what's going to be the path coordinates. Also, path coordinates rotating in a circle, right? You can tell right there. Going in a circle, path coordinates again. Here's you see a spring, work and energy. We really, really, really don't like. I guess you could probably write a problem in just the correct manner so that you don't have to deal with the fact that a spring, the force of a spring changes obviously with displacement. So that's not a constant acceleration problem, which makes using either impulse or momentum or Newton's second law makes it difficult. You'd have to integrate, right? You don't have a constant acceleration going on. It's a work and energy problem. Here's a combined impulse and momentum, maybe a little bit of work energy going on there because you see some springs. More springs, more work energy. Kicking going on, that sounds like impulse momentum even before you see the title. It says impulse momentum. More springs, it's work energy. Impulse momentum, people like this problem. There are all kinds of variations in all kinds of books. Or jumping off of boats and kind of thing. It's kind of an interesting, or they're walking along a boat, kind of interesting. Working energy, impulse momentum, working energy, impulse momentum. You get the idea. All right. So, and also, by the way, if you're on if you're in my class, it's available to you. But also, if you are on the recitation thing, there's the Missouri University of Science and Technology. Some professor, it hasn't been for a while, has been on there and has a website and put up all of his exams for like lots and lots of his exams. So you might consider, they're usually fairly simple, but I think they're good. They tested. There's also the solutions on there as well. Shortcuts and stuff that I wouldn't use, but best to not read these. Try them. So if you want to do some of the problems are seeming too difficult or whatever, or you've already used them up. Here's a whole bastion of them, and so like I just grabbed some off the top on here, so we could try any of these. I'll point out to you the link into the recitation if you are up there, or we could also just take a look at what the URL. I think it's useful links and resources. There's the Beer Johnson stuff. There's the Shams outlines. And like her playlist. She has very short videos. I wish I could make videos that short, but too long-winded. Okay, this guy from Washington University of St. Louis is the funniest guy. Well, at least one of them. There's a bunch of old exams right in there, but this guy's hilarious and does things with often Captain Underpants is the hero in here's the link right here. So you can see that there's lots and lots of problems. Each one of those is a problem. So anybody given me requests? What would you like to see? We'll go back up to the top right here. We can pick something up. Yes, sir. So a dependent motion problem. Try. Let's see. Okay. Camera. You didn't know my location. Oh, there I am. Get this right side up. So we are in chapter, that would be chapter 13, I think. Work and energy, sure. And power going on here. I would also point out, again, I say this in my class, but we have other people here besides my class. Don't forget the textbook. This is a great resource to problems, and if you want to do well, is to go like that right there and try that problem out. Try it for yourself. So, like, while we're here, let's take a look at this and do this problem. We'll waste it, but it might as well put the thing out there and model as you, if you will. So you should approach any problem. So let's see. Got to draw the thing out. Up first. A lot of times it's actually better to just kind of like do the tangents of these and come down. It goes into the body. And now, like that right there. There's our motor. I'm not sure why those things are there. They're kind of unnecessary, it looks to me. I should have put that guy in there. C, D, and let's see. Let's get some things going on here. This guy. Seems like a mean name to me. Almost dumbwaiter and lazy Susan. Very nice people sold things. Convenience. So I guess the weight of the dumbwaiter is 600 pounds. And whereas the counterweight, C, is 800 pounds. Doesn't look at it. Determine the electrical power. So we got ourselves a find symbol for power. It just kind of looks cool. I don't like it. A, speed, V, D equals 8 feet per second up. Instant. The instantaneous velocity is 8 feet per second. So it must be still going upwards, and an acceleration where both are going. Okay. And A, D is equal to 2.5 feet per second squared. Okay. We don't peak. Test yourself, right? I said in class many times, you're going to prepare for an exam, you got to practice like you play, right? Simulate the exam to best your ability. You didn't know. You got to sit here. And also, one of the biggest exam piece of advice I could give anybody: don't sit there and hoping that a message from God's going to come down. Don't wait for it. It'll happen while you're writing stuff. God doesn't mind. He'll tell you while you're still writing. Start writing and do stuff that you know how to do. Right away, tell it's a pulley problem. Let's start out with our pulley problems. Boom. That's a good place to start. Right here. C. Right to there. I guess I could do it up to here. There's no, so I don't know why I'm putting it up in the middle. You just put it right there. SD. And then I'm going to pick a spot somewhere on the rope. Because we're going to need, all right, so we're forecasting here. I just jumped right in. So should mention that I knew when I was talking about power, I use the kind of power that's force times velocity. Power is equal to force times velocity. You can also do power is also equal to torque times RPM, but we're not really doing that kind of before we do this. So what force times velocity, and so we're going to have it's going to be the force, the tension in the rope. So we now need the tension. We need the velocity of the rope, the tension of the rope, and the velocity of the rope. We get that, we're golden. So we're going to have to try to find that tension. The only way you can find tension is cutting a rope. Got to cut it apart to be able to see it. Take that spot, and I'm just going to call it, we already used C. Where the hell B go? It went right there. We decided that's going to be B. So go to SB. Now, to do our dependent motion, so we'll call it DEPMO. And because that sounds cool, it's going to make us feel better about doing it, something we don't like doing. Do this carefully and identify that there are two ropes. So you can do that by just following the rope along, and then you go up, stops right there. Another one picks up, right there. Okay, so we're going to have two equations. If we have two ropes, we'll start out with L1. It's going to be 1, 2 SCs. They shrink at the same amount, so there must be two of them. And only one SD. I think I'm going to go downwards with my thing, so I'll go jump over to the right a little bit. I'll go, here's my other rope. 1 SD. And then, why did I write, it looks like a D right there, doesn't it? B. I turned a B into a D into a B, which if you try that, like now you guys don't have that kind of pleasure because all your grades to your parents when you're in high school were all electronic probably. But back in the day, they gave us little cards, and you could, sometimes they'd be handwritten. That's how old I am. And you could totally turn that D into a B. Twice. So anyway, you get this length 2. SD plus SB. You can kind of do this. You can see where that's going. You've done enough of these to be tired of them. And so now we got the relationships between the points, the dependent motions. So the acceleration and velocity of D and B are going to be the same, but in different directions. C and D. C is going to be twice the velocity of D and twice the acceleration of D. All right, so in the first problem here, we have, it's going to be, because it's constant velocity, we have a Newton's second law problem. Statics problem. Not a big deal, but we want to find the tension in this rope. We don't know the tension in the rope, so let's find the tension in the rope. So this part A, still going to have power. It's still a power problem. There's just no acceleration, so it's not a Newton's second law problem. So in part A, we get an FBD. And just because it's left to right, I'll go that direction right there. I don't have to draw an IBD because it's not accelerating. But we do have to cut the rope because you can't find tension. You do inside the rope. So you have two of them, so we get 2 FT, and then we're going to have WC right there. Because it's in US units, we'll just use, we don't have to do the MG. Just, I know that might seem obvious, but we're trying to organize our thoughts, and some people can get like, shouldn't that be MG? I'm like, yeah, we usually use that with SI. We already know it's going to be the weight. And so some of the forces in the y direction. Seems silly to do it, But this helps to organize our brain, be on the lookout for things that we might screw up. And so also, let's define what our directions of our things. 2ft minus wc. I could keep this as a, these are hard. I could keep this as, I'm trying to see if there's anything else. I could keep this as a variable, but I do know what it is. So, oh, by the way, I should make this ft1. Sorry. It's gonna have, these ropes are going to have different tensions. I should remember that. Yeah. Okay, cool. And so that's going to be, what did I say, 800 pounds? So ft1, I think I could do this, 400 pounds. And then go the FBD of the other piece. So we have FT1. Here we're going to have FT2, right? So it's because we're going to it's both off, one there and one there. Weight of the dumb waiter. Still makes me feel like we're being mean to this waiter. So we're going to have, again, I could probably keep these as variables and write that out, but let's just go ahead and put in what we already know. We have 400, this guy we just found out over here, T2 minus the 600. So let's see, did I do anything? No, I think I got it. FT2 is therefore with 600 over there, but it's going to be 200. Did I get that right? Here. I see a lot of people that just want to skip steps on things. I've screwed things up because I skip steps. I've made so many mistakes, I'm the perfect professor because I can testify what not to do. I even have a poster in my room that you can come by anytime see of a ship that's sinking. It says, mistakes. It could just be that the purpose of your life is only to serve as a warning to others. Skip the steps. Anyway, we're now we got the two. And we know right here, this is going to be 200. So we have to do a little bit more. Actually, we know that in feet per second at a constant, and therefore it is, we could do right over here, that B is going to be negative VD. So it's going downwards at 8 feet per second. So I'm going to draw the rope here, and I'm going to make a little, that makes it, I cut the rope right here. So that's sort of like point B right here, where we have T2, and we also, it is moving at VB. And over here is the system. So the positive, this is positive energy rate being added to the system that I haven't drawn the rest of. Right? System boundary, I'm at the system boundary, and the motor, and as you would know, the motor would be putting energy into the system. By the way, just like a Prius or some generative type of stuff, where the motor could act as a brake and could be generating electricity and therefore taking power out of the system. And you'd be able to tell by seeing that these would be going the opposite direction from each other at the boundary where the most to the system. Just want to point that out, organize our thoughts as to what's taking place as a means of figuring. So anyway, the power here is going to be equal to FT2, and this is a times, not a dot. So we would say that that's going to be 200 pounds. I'm going to put 200 pounds times 8 feet per second. So you would get 1,600. I like to say foot-pounds, but that's a weirdness of me. Some people like pound feet. I don't like them. I like foot-pounds. Why isn't it negative? Oh, well, I'm going to say that, well, first off, that I kind of know, but also if I needed to, with the signs with each other, although it is not a work energy problem, it is similar to a work energy problem in, in terms of the concepts that we have. Energy problem would be between two states, right? We'd have state 1 and state 2 usually. But that was so hard. Well, I'm not taking the absolute value, but I'm going work as we defined it was integral force dot dr. And the idea here is that the force and the change in position are dotted against each other. So just as with a dot product of two vectors right here, we would, like if there was a magnitude this and a magnitude that right there, there should be a delta right here. We do a dot against them. So if the dot, and that's like a cosine. So if the cosine, if there's a 0, right, if they're in line with each other, the result is a positive value. So the fact that we have these two things going in the same direction, even though one of them is negative, they're both negative, so they're negative, we might cancel each other out. You can think of it this way too. That we're putting that energy into the system this way. Rate of energy, I should say. And if we wanted to get these into our favorite units here in power, we would divide 50 foot-pounds per second per horsepower is a unit's worth conversion. So 1,600 divided by 550 is 2.99 horsepower. And one of the reasons we might want to do that is, I think it's really important in engineering. You always have something to compare a value to, because it just be some arbitrary number. I mean, what the hell does the number mean? So you have something to compare to. So many people will know, like, that's not a great, but a lawnmower, right? At that size, right? Yeah, a walk behind lawnmower, not the riding one. But yeah, it's good. So it's good to have it some means of like, okay, how much is that? Part B in this is where we really do a little bit more of our dynamics. And, maybe just out of curiosity, we check and see if we got that right. We're feeling pretty good about ourselves at this point. There's one reason to do it this way. There's a certain amount of satisfaction that you get. A little bit of confidence, and that confidence will really help you. You want to build that confidence. Anytime you're losing some confidence, you'll go back a little bit, do another problem where you get a lot of exam results are about how much confidence you have going into it and how you can maintain that confidence even when you hit a speed bump. You completely had like get my PhD in the first class. I came back after 20, no, not 20, it was like since taking an exam, and I thought I was ready. I was already a professor, teaching as a lecturer at least, and I had to go to the bathroom, just wash my face, stare at myself in the mirror, and just do it, man. Just, get out of it. Slap your, you got to figure out a way to do a reset. I've been there. I know. It ain't fun when you have that kind of, but resiliency. Believe in yourself and grab a hold of stuff that you can. Sorry to deviate. Let's go back to this thing. And part B, we're big difference. So now all our free body diagrams should have their second cousin, the inertial body diagram, also known as a kinetic diagram. And so I think our book uses kinetic diagram. So let's set this thing up. Don't skimp out. I guess you could have drawn, if this was I don't think anybody's asking a problem where you're going to have to do both of these. It's helpful in a reviewing to look at both of them. So we're going to have a question here. Which direction on the IBD does C go? We could do this fairly easily with right over here, right? So D is going upwards, right? And accelerating upwards. So C must be going downwards. Okay? We're going to go MC, AC. And as we get to that spot right there, say, well, we don't know AC, but we could use the kinematics that we got from right here to find it. We know that it's going opposite direction. We just established that, and 1/2 of D. So I could write that somewhere. I could write it up here. On an exam, so maybe we're going to leave this here and write the thing out. So we're going to take the sum of the forces in the y direction equals mass times acceleration in the y direction. We've defined upwards as being positive. So we say we have 2ft1 minus, and I'm going to go ahead and put the values in because I did before, so I'll be consistent. This was 800 equals mass. So instead of playing around with writing it out separately, I think this could save you a nanosecond in here. Anytime you see mass and you're dealing with US units, just take it and divide by 32.2. Just get used to it, right? US units, don't even need to write out what the slugs are someplace. Your professor says to do it, but I'm not sure why they would do it. And then I'm going to write down the AC. Oh, boy, silly mistake. Angry at myself, talking and not thinking. You don't have that problem on the exam. Reason to help, a lot of times it's to help you figure out the signs. A lot of times to break down the thing into components. And I just made a big old costly mistake right there. Minus into the thing. All right? And now I don't know AC, so I'm going to go from depth mode, and I'll say that acceleration of C is equal to 1/2 the acceleration of D, which is not hard to do because that's going to be 8. Therefore, it's 4 feet per second squared. That might be a little over the top writing the thing in, but you do need to communicate. And it would be nice if you were to do it in such a way that the professor could read the thing you're doing. Not over here, over there. When you get it wrong, I got to go, what the flying? Oh, it's over here in the corner for some reason. They did the thing over there. It's this right here. I'm still thinking, hey, it's Friday. I get to do more work this weekend. Excited. It's kind of sick idea. Thank you so much. All right, so now we could go, we could put this back into there. So what we got, FT1 is going to be equal to 800 divided by 2 minus, I'm going to keep these 832.2. I got 2 in there, that's from right there. And then times our 1.25. Interesting that the acceleration makes the cable tension less. Okay, yeah, I can see, yep, because he's moving, yep, he's moving down, sure. So 800, I can't remember if I did this right now, okay. All right, so somebody else hopefully somebody else is calculating this with me. Did you get 384.5? At the end, I probably screwed something up, but yeah, whatever. We get to the next part of it where we do the other free body diagram. Leave enough room for myself here. I'm going to have a step going on there. It's in there, but I'm a terrible, terrible hypocrite. No, actually, I'm a really good hypocrite. Let's see, that's what I'm good at. You'll know when you're a parent what I'm talking about. So this one's going upwards, right? So we're going to go MD times AD. Sum of the forces in the y direction equals mass times acceleration in the y direction. Is in here. This was my 384.5 FT2. I said 40 right after. How many people said when I said WD just went 40 right after? You should soon. You're supposed to be engineers, right? WD-40. Duct tape WD-40 is all we really need. We can make space shuttle get up to Mars. It's probably not true. This is 600. I think we're done on the left-hand side, which is the whole purpose of these diagrams, is to help to be our guide over here. It's going to be equal to positive, there you go, now your brain's working, 600 divided by 32.2. And then AD, which they already gave us as 2.5. I almost said 8 again, just so you know. Just so you know. But it was because of you. I was able to, I remember. I don't want to let you down. I don't want to let you down, man. Let's do it. Maybe. All right. So I'm going to, okay, 6. Positive over the positive. And then we're going to go 600 to divide 2.5 times. Scared. I'm scared. 262.1. It's like a Muppets. That was like Kermit. Yeah. All right. So we our last feats of strength is going to be the power. We'll take our FT2 and the VB should equal VD. You're thinking that I just said VD and laughed inside my head. You'd be right. So there's all I care. So this is 262.1. By the way, notably, two problems very similar to each other. Kind of what they wanted us to do was to compare the two things. It was 200 pounds when it wasn't accelerating, that cable tension. Now it's 262.1. Able to compare things that's a sort of, that's insightful. And we can go ahead and because we already know that we want to have it in horse power. So we can see how many horses it would take. In my class should answer this next question, but so we want to give everybody else a try. How many horsepower is one horse? So close. He was close. 15. Google it. I don't know. I don't have any proof on this. I just know what the interwebs are telling me. And the magic man, he says it's 15. I'm like, Like, you know, what the engineer is going to ask? What a real engineer is going to ask is, okay, well, no, what kind of horse? Yeah. Size of the horse. How old is the horse? What has the horse been eating? This is mood. Did the horse get purchased by two Long Island hippie wannabes who moved to Western New York and purchased about the kind of horse you would expect that rural people would sell to a couple Long Island hippie wannabes in 1991, moving to, and the answer would be, that horse is not a 15 horsepower. Not at all. And his name was Rusty, and he was a good horse, and he only died like 2 years later. Several $1,000s in loans and debt. My parents were morons. Thank you for your next question. Okay. We can do a collision. I don't know if I can get it right. Oh, by the way, we didn't see if I got it. See, how did we do? How do we do? Reflect and think onto this thing. 3.8. That same one we got right? Felt good. Felt good. Can be an enjoyable thing. I got to tell you, also, I think I have mentioned this before, probably in here. An engineer. It was a good thing on one level. I didn't like him. We became lifelong friends later on, but not at the time. But would race. He would make me race. He said, okay, we're going to do this problem. Go. And we'd race. Tell you what, get a study part that pushes you. And we can really have a problem. Maybe we should keep going with this theme. Using the book. Or am I using them up now? I don't know. I don't think people use the book much. That's my guess. 2 confessions time. You don't have to confess. I am not, well, I've almost said I'm not a fool. I am not that kind of fool. Do the hardest problem? Oh, we could do this now. Hard problem. But several hard problems. Okay. All right, so these tend to be really long problems when you have 2 of the balls moving. Most of if you're going to ask a collision problem and you're a professor and you're not, well, I don't want to like paint myself in a corner here. Generally speaking, this is too long of a problem for an exam, unless you're only giving 2 problems. This is at least a half-hour problem, for at least. And then if you mess anything or you're not really strong in this, it'll be a longer problem. Oh, no, I'm saying when there are 2 velocities and they're both going in the same, and they're both going in non-normal axis. But one benefit to this is that this is not on an angle. That right there adds a little bit more complexity to it and adds a little bit more time, especially if you fudge anything up and you gotta, like, you know, sometimes you gotta use your eraser, but I would definitely give you advice, if at all possible, do not use your eraser. Just draw a straight line through the thing that you just did, get more paper. Because professors want to measure your mastery of the material, and even your mistakes are demonstrate, even that you recognize you made a mistake and started over onto the other thing, you should be able to get some credit for the things. If I can't see what you did and then you did something wrong, I don't know, you might have been on the right track. So sometimes I'm like, you got the wrong thing, but you were on the right track until you changed your mind. Get some more points. Get the points you deserve for the knowledge that you have. But if you screw something up on a really long problem, a lot of times you miss it. So this is a classic problem, and I think, try it. Might be a little tough, but hopefully, I don't know if we should do it all the way through, because it might not be the most efficient amount of our time to go painstakingly through here to get to a result. And I could be saying that because I'm afraid I'm going to screw it up. But let's just try it and see, right? And this whole process right here is repeatable in every single class that you take, every single engineering class you take. Because I tell you, one reason why I volunteer to teach dynamics is because I feel like I can have a positive impact on students' lives, not just in terms of dynamics, but in other engineering courses. Because when I started taking dynamics, statics and dynamics it's really where everything changed for me. It's like my whole life changed. Started having some success, and that success turned into more success. And it was like, I want to be able to share that kind of feeling of new confidence that I get from this. Okay, but by the way, let's talk about the problem. A has been dropped down and is now moving when it's this direction. VO. I would call it A, but I'm going to change that. I'm going to change it. I don't like that they call it O. I'm going to call that A1. And so this is A, and this is B. And now let's see what the information is. They're probably, by the way, this might be a symbolic, no, it's not a symbolic one. They gave it a value? This is interesting. They didn't give this a value. It must cancel out. They didn't give us the mass, but they tell us it was the same. Identical ball. So the M's equal to M. So MA equals MB. That happens a lot. And then you just put some trust. It's going to cancel out at some point. So we'll be on the lookout for that. Inextensible robe, just touching the cord, acquires a velocity of VO before striking ball. B, assuming a perfect elastic. Okay, so E equals 1. Not as satisfying in terms of problems right there. Sometimes that coefficient of restitution is the extra problem. But we could say when we'll write this out here in a second, we could say that the let's go B2 minus VA2 is going to be VA1 minus VB1 is equal to 1. Remember that the coefficient of restitution represents the ratio of the negative relative velocities after over before. So that's a lot of words. All right. So notably that the A and the B swap places. That the after is on top of the before. Them swapping places means it's negative. Because if you just had one ball and you bounced it, it's obviously its velocity afterwards is going the opposite direction after the thing. And here's our relative velocity. Okay, and it's before is equal, after is before, because we expect generally this is going to be a smaller number. In this case, they're an equal number, because this is a perfectly elastic problem. And no friction, there's no losses. Determine the velocity of each ball immediately after impact. So I'm a little, okay, that's it. They did everything in terms of VO. So I guess I will just go ahead and stick with VO, even though I don't like it. But that's going to be, we're going to use every VO as a variable, just as a, right. Okay, so the thing to do, I think, is to, let's put this over to the side. Do the 3 diagrams of an impulse momentum thing. So we have initial, impulse, and final. In some part, I'm doing this because it gets us into a routine, right? It also helps us to organize our thoughts into the, what's that? Sure. Calculator underneath it? Oh, there you go. I didn't see the, somebody's calculator up here. CB, anybody know a CB? I'm sorry, this never stops amusing me that this used to be the makerspace. And when they did, everywhere you could see were those yellow things hanging from the ceiling of the tower. Everywhere. Techs come in, we turn it into a classroom. Dr. Asaki and I think, are the first ones to walk in on. They forgot. No. Okay, so anyway, and so what we could assume, what we can see, we can prove it to ourselves. This is going to be a 45-degree angle, and so we would call that the normal direction. And I'm going to put a tangential perpendicular to it, but it could go downwards. It could go it could go over to the right if you wanted to. Instead, I just made it up and to the left. Doesn't matter. You could even draw it right in there. Can you technically get away without doing this, without drawing this diagram? Well, you can't if I write in the question, you must draw a impulse and momentum diagram, then no, you cannot get out of it. But generally speaking, I want you to be doing this anyway to try to organize your head. All right, so this one is going downwards that way. Initially. So he's going to have a mass times his velocity in that direction, but I want to do it into these components right there instead. So that's going to be our MA times our VN. And there's also going to be, in the tangential direction, MAV tangential. This guy's going to have an equal and opposite impulse. I'm not going to take off points. I say that, but no, I won't. I'm not looking to take off points. Labeling that, but it is good to think your way through and say, okay, these are impulses, but because I've chosen the system and it's not together, cancel each other out. Here, we're going to have a couple things we know, so I don't have to draw things I know not to be true. First thing I'm going to do is I'm going to draw in the tangential. I know it's going to be MAV tangential, and I know those are going to be equal to each other, right? So I know that whatever this velocity component is going to equal that velocity component before it equals after, because there's nothing in the tangential direction that would cause it to change. There are no impulses in the tangential direction. So it must have the same before and after. The same thing true right here. There's going to be nothing in the tangential direction because there were no impulses in the tangential direction to cause it. You're going to go try to think about things in the real world and you go, I could think of scenarios where there would be if these things weren't particles, which don't have any size. If these were let's see, tennis balls, and they were spinning. And now in the tangential direction, they could have some impulse as they hit each other, and they would be influenced that way. But there's no friction. They said no friction. And even though we show them having a size, they functionally have no size. And then, so here is sort of a dilemma that I have, but I'm going to solve it in my usual way. It's not sure. The reaction of this, we can start predicting what direction things are going. We could. And everything might turn out all right. But I found that we can, what you're going to, if you predict something and then get a negative number, you predicted it wrong. Right? So that could happen, right? So what I instead do is I predict, even though I know it might not be true, that both things will move in the positive direction, right? Like there's no way this guy right here is moving in the positive normal direction. But I'm going to pick it anyway, and I'm hoping I get a negative number when I'm done. That'll tell me I was wrong. I think that's the better logic to apply as opposed to guessing in other sets of circumstances and getting it wrong, and you get a negative number and you go, oh, wait, so does negative mean in the negative direction, or does it mean in the, oh, no, okay, well, I'm not going to mess with it because I've been there. I'm guessing the positive direction. M, B, V, I think I got to go B with this because I can't keep using the VO. Hopefully, we'll find out what the B is, and it'll be that's going to be in the normal direction. And then this guy too, I'm going to take it M A V A. It's going to make him. I like my system better than their system. Yeah. They do a prime onto the thing. Put a 2's in there. I'm squeezing 2's in there, sorry. Actually supposed to be A2. All right. Let's see if we can get this going on. All right, so we do the, this right here corresponds to this right here. Fundamental impulse momentum equation that we use for this stuff. Okay, so I really messed this thing up by choosing this actually in this direction. It would have been better if I had chosen it, but I'll just stick with what I have. So this is going to be in the n direction. I'm being specific there because these are vectors and we're only doing stuff in the normal direction. So as I write that, I should also, at some point over here, I should have said that VO T was going to be equal to VO times the, let's see, I got to try to think of which way I want to decide to make my angle. I guess I'm going to make that angle right there is my 45 degrees. I decided this has to be 45 degrees, right, because it's halfway. I think I'm right. No, it's not. Okay, so the angle, let's see. It ends up being 30 degrees. Wow, I thought it was 45. All right, so let me explain why. Can. Yeah, there you go. All right, so the hypotenuse is going to be 2 radii, and the side opposite from this angle is going to be 1 radii. And we can know that's going to be a 30-degree angle, right? Silly me did a, don't be like me, guys. I said kids, but that seems like kind of condescending, doesn't it? That's radii. Radii, you could find out what the angle is going to be by taking the inverse sine of 2r, which is the hypotenuse, and you should end up with 30 degrees. So, wrote that in a very inconvenient spot. I could write that V tangential is going to be a VO times the sine of 30 degrees. VO normal is VO cosine. So I get over to here. I'm going to negative MA VO normal. So that's going to be VO cosine 30. And nothing else on the left-hand side, because these cancel. This is the only thing going on in the equation. It's going to be equal to, now MB, I'll down this one here, times VB2. So it's actually the entirety of VB2. So I could have left that off. I will leave it off. VB2. It's positive, and then this one's also positive. So, plus MA VA2. Right. So, one thing we know is that all these masses are equal to each other, so we can get rid of them. VO cosine 30 equals VB2 plus VA2. That's equation 1. Now we have the coefficient of restitution as we had up at the top. I'll rewrite it out here. We said that E was equal to 1 and it was equal to V2 A2 normal divided by V A1 normal minus let's put the end in there. This guy is 0 though. So I say VA1. Which I know, by the way, I can substitute that right away. VA1 was going to be V. Oh, by the way, when I do this right here, I have to use the signs that are in my convention. My convention signs over on here in this diagram is that VA1 is going to be a negative VO normal, which is a negative VO cosine. I could have turned that into a number if I want to. Okay, so that right there equals that is going to be equal to both of these guys, right? So now I'll turn that back into, got rid of the normal thing to be match up with this, and then minus VA2 normal. And now I have 2 equations and 2 unknowns, if I did this correctly. Difference is that negative sign right in here. The way that I will approach this to solve it is, it depends which one I want to solve first. Do I want VB2 or do I want VA2 first? I'm going to go with VB2. No, VA2, I guess. Okay, so I go VB2 is equal to V2N to the side, so it's going to be minus VO cosine do this back in to sine of 30 VA2N Is that going to be true? I don't like that. Doing something wrong. Same equation with that being different. And I went to B2 and I put it back into there. Took the A2 and I brought them back over here. And I decided, what am I going to? I'm going to keep going with it, but I don't like it. Algebra. Really don't want these two things to cancel out. And they're looking like they're going to cancel out, right? Because I'm going to bring this as the positive over onto that side. And now it's going to say VA2 is 0. True. Something else. Let me take a peek. Right? This is what you do, though. You get to a place where you get stuck and take a look. So they make it look like so easier here. Tangential component. Oh, wait. Oh, no, that's because it's the sign. Okay, no, that's fine. Okay, cool. Some of balls A and B. The chord is in there. Oh, messed it up. Yeah, I should have practiced beforehand. Right? But I tell you what I just did right there is I'm modeling, I guess, like you screw the thing up, and now you figure, be on the lookout for something. I'm not necessarily every problem that exists. What I did wrong is there is impulse right here. I didn't draw in. I said to do this, and then I didn't follow through. I could blame myself for talking through the thing. We have this going on. T, and we can't go delta T or make it integral, but this one does not cancel out. So we have to do something with it. And this one what this decided to do as its remedy was to go in the X direction for the components, so that the T wasn't in the way. And you'll notice you can establish some behavior that has to be true afterwards, and part of it is in the MA. It's in the well, it's in the X in this one right here, and but you have in this instance right here, because I guess you can't go upwards, B can't go upwards and it can't go downwards. You've established that it has to be entirely in the X direction. Further with it on that problem, let's do something else. But I tell you that this is a good process. Even though we didn't have success on the thing, we yeah. We stopped ourselves from perhaps making other mistakes by identifying that we just ran right past that it has tension on it. Yeah, don't forget to sign in. You can sign on the back too. I've been scanning those and sending them to the other two instructors, just so you know. Want to do another problem? We're going to give up. You can see how we have another type of problem. Newton's second law problem. Number 2. With my homework. You can pretend they're not touching a little bit. Did you see the video of the? Well, I could give you a little hint on there because we talked about it a little bit. I talked about it. I know I made the thing already. Together, don't I? Yeah. And so you had is this A and this B? Uh, Diagrams. I think I could do this. What I'd say to do, I think, is to leave a little bit of a gap in between them so that we could go what happens to A first. Of course, I shouldn't draw that in there. And here's the ground. Hit each other here. So it goes down this way right here, and it's going to come back up that way. We can predict right here. So they have their own coefficient of restitution, right? So you're going to say that this was instantaneously going to hit and then rebound right up here, and just in the next second, this is going to be coming down while this is coming up, right? And now they're going to go boingy boingy, and you're not quite sure what direction they're going to go, so you usually both go positive up. And so this MAVA2 is MA. Two, this is M, and just to keep them, I think I got the numbers correct, or I seem to recall stammering back and forth what to call that. I decided to call it 2, and I decided to call it event 2, so that this would be MAVAE and MBVB3. And I think VB3 is basically what we're trying to find. Or how so we pretend like the balls don't have a diameter. What we have to do then is just go VB4 y squared VB3 y squared, oh, not plus, equals minus 2G delta y was what we were. Say, when that goes to 0, we can find out how high. I'm just trying to give like a sequence of events. Well, you're right. And here you can't use this moment diagram for anything because we don't know the momentum of the planet Earth. So the diagram is I'm just putting the diagram to force you think your way through the process of the thing. You would use the E of which essentially will be negative V 2 over VA1. Because you could put you could use right. I just omitted the velocity of the ground. Yeah. And then right here is where you would you have an equation right here for in terms of their signs and they give them right, but then you also have the E again where you have what let's say VA E minus VB3 E B2, which is actually going to be 0, right? VA2, which is what we just found up here. And then make sure that you put the signs in here as they match in the diagram. So this one will be negative here. Oh, I said it was 0. No, it's not 0. This one is good. This one is still going down. And the reason why we could do this, because we're saying it's this instantaneous, nearly instantaneous thing. Even though I think it probably, in reality, would have some amount of influence if there was a gap. Personally, I think so. I think if you could keep them somehow, magically, touch it, put a little chewing gum, I bet you would have a different result if you had like a little piece of chewing gum stuck between the two. So it didn't have the gap. So they were kind of acting like one mass. And then the chewing gum would let go, obviously, because it's not that sticky. But you might have a different result off of the thing. But it is kind of cool to see that video of the lady trying to think, especially with it has the 3 of them. Yeah, golf balls, yeah. Do that at some point. But then, do you see I made the SolidWorks one of it? Yeah, which is cool. This actually worked. But I don't think the numbers were. I checked the numbers. I actually used the right numbers. Didn't match. Just the nature of, using computer simulations. Because what the computer simulation is, this is an excuse. It could always be an excuse, is that nothing is truly round on a computer. It always has facets. Facets there are. And when you give it a command in a simulation thing about, like, this thing is not allowed to pass through that thing, it really do some amount of, like, calculations. Is this thing touching? Really? Is it touching? When does it touch? And how much does it touch? And then you also internally are giving it, okay, it has a coefficient of restitution of this. It has to make, I won't say make decisions, but it has kind of like conventions that it's running through, and the fact that the two things are round. In theory, unless they deform, they only have one contact point. In reality, things deform even just a little tiny bit, and so it isn't just one little point. It's actually like a little flat surface, a little circle that's actually between the two things. So the computer simulation doesn't have the ability to do that. It's just going to do the best it can with an approximation. It knows the center's distance of the thing, and it tries to touch and how long. But the real one has residence time, infinitesimal amount of residence time with actually squishing and then rebound. And then, but you would think, okay, and then now, so we have the one that's done, these attempt to do in education. If there's an opportunity to have a lab with a class, so you can do the magic combination of doing an experiment, doing the thing by hand, and doing it on the computer. And you can try to reconcile what those three things are going to be. And it's a sort of quite an education when like you find out like you never make those three things quite work out, but you really learn a lot by like the differences. Especially if you don't just do it once, you do it a couple times. You change a couple things, see the cause and effect of the thing. And then you can start to get an idea of why you make simulations. You don't make simulations necessarily, sometimes you have to, but you try not to have to use a simulation to get an end result. Like, here is the number that I am predicting. If you're going to the moon, you want to make sure that your simulations land. Yes, you can, but many other the complexities in. But this is an interesting one because you could do it by hand. You could, maybe we could find an experiment to do with the thing. Restitution is probably more complicated than we tend it to be. I bet if you tested it a bunch of times, you wouldn't get the same result every time. There'd be some small little changes and things, and anyway. And prep, or we're burned out. Hopefully I helped with the homework problem. I got to do some homework problem fixing. I think you're given initial height that's dropped from. Okay, so you use the same equation here? Yeah. It's interesting that because of that.
Kill it. Not my best work. I don't know what my best work has ever been. Getting better every time. Goodbye.